So in our last video, we started talking about torque and torsion and our applications for that. And really one of the biggest applications that we use this for as engineers is in power transmission, right? So these circular tubes and shafts are often used to transmit power, getting power from a motor to something else, right? That rotational movement through that circular shaft so that power can be moved from one place to another. That's something that we super care about as engineers. We use it all the time. You might have an entire class dedicated to energy, power, and motors, this kind of combination of things. So in this power transmission, right, we use these circular shafts to transmit power, where we have our power definition is just work over time, right? If we want to define work to relate it to our torque, work is torque times the angle of rotation. That's my little shorthand for angle, but I could really just call this theta, right? It's torque times the angle of rotation. So we can combine these ideas of torque and power by removing that intermediary work and relate them together as our power equals, well, let's do it this way. Power is work over time. Work is torque times the angle of rotation, theta. But if we combine these together, power is torsion times theta over t. This theta over t, d theta over dt, is also the same as angular velocity. This angular velocity is a lowercase omega. So it's kind of a fancy W. It's not really a W. It's kind of more like a twisty, fancy W, but it's a lowercase omega, is angular velocity. So sometimes we'll see this power formula simplified as power is torque times the angular velocity, but we often don't use it in this form. We're more likely to translate it into frequency. Because an angular velocity typically has units in radians, like radians per second. And that's not something super real world that we use all the time. We often use frequency. Frequency, which has units of like RPM or RPS, revolutions per second, right? Or cycles per second. These are much more common, and this is how we often rate motors, right? Through RPM. What RPM is it going at? What is the frequency of that motor so we can get a torque and a power calculation? So most commonly, this power equation that we're going to use is 2 pi times the torque times the frequency. And that's so that we're basically converting the angular velocity from radians into revolutions. But this equation gets us there. This equation does that conversion for us. Right, so it's this 2 pi times torque times frequency. And I do think it's important we kind of talk about the units on this. We touched on this frequency we see in RPM, RPS, cycles per second. You'll also see that cycles per second sometimes as hertz. Like the car rental company, Hertz, abbreviated HZ, Hertz, which is just a per second. Like it's a cycle per second. 1 cycle per second equals 1 hertz. So you might see that appear as your frequency units. You'll also might see this revolutions per minute, revolutions per second. Those are very, very common units for our frequency. Our torque here, You're going to see in units, in SI units, you'll see this as Newton meters, as we're used to. And in English units, English, engineering, US customary, FPS, you'll hear it called all those things. You might see EE, FPS, English, US, customary. All of those are names for the non-SI units. We can't even agree on one single name, apparently. We have to be so different from the standard SI units. That our English units, we've often seen the kip inches, right, in the problems that we've been solving before. But just know that pound feet or foot pounds, this is also a super common torque unit. So it could be either one of these that you see that we're working in. Just keep your units in mind because there's a huge difference between a kip inch and a pound foot. Right? It is not like the SI system where you can just be off by a factor of 10. You're off by a lot more when you're converting between kips and pounds and feet and inches. So bear in mind that you can have either one of those as your common units for torque. Which makes our units for power extra interesting, right? So power in SI units, the SI unit for power is a watt. We measure power in watts in SI units. Just like your light bulbs are measured in watts, it's a measure of power output, where 1 watt is the same as 1 Newton meter per second, which checks out, right? Our torque is in Newton meters and our frequency is in per seconds. So Newton meter per second is going to give us 1 watt. Very easy conversion, very easy to think about. If we just know a Newton meter per second is a watt, we have our units all straightened out. Power in SI units is watts. But in our English units, we like to make things a lot more complicated. So the English unit for power is exactly what you think it's going to be. If you're a car person, it's horsepower. That's our standard unit. Our standard unit for power output is horsepower, right? You see that rated on all your motors, your cars. This is actually the English standard, horsepower. But the conversion to horsepower is, of course, not as nice or as clean of a conversion. So 1 horsepower, 1 HP, I always do a lowercase HP because an uppercase HP makes me think of hit points in video games. And it's not that. So I usually do a lowercase HP, but you can write it uppercase. 1 HP, 1 horsepower, is 550 foot-pounds per second, where we have to use this foot-pound torque, and then again, that per second is coming from our frequency term. So 550 foot-pounds per second, if you want to convert between that torque frequency calculation and horsepower, which is the standard English unit of power. It is what it is. I wish it were simpler, but it's 550 foot-pounds per second. That is a horsepower. Let's go ahead and take a look at an example of how we might use our power transmission with our torque. In this example, we have a solid steel shaft transmitting 5 HP from a motor. If that shaft rotates at 175 RPM and we're given an allowable shear stress of 14.5 KSI, we want to determine the required diameter of the shaft to the nearest 1/8 inch. Right, so it sounds like a lot of information, kind of an info dump. Our picture here really isn't all that helpful, and it's not just because I'm not a great drawer. It's also because that's really all it gives us, right? It gives us a little motor here, and it's attached to a belt that is rotating, right? So it's rotating this belt here. There is some torque. That's what we're given. So if you're ever given equations, what I always like to tell people is write down everything you know and any equations you know that could be applied to stuff. Right? So even if you had no idea where to go with this, you could say, okay, well, I'm given the power is 5 HP. That's something. I'm given that the shaft rotates at 175 RPM. And even though it doesn't tell me what that is, I say, oh, RPM, I know from that unit, that's a frequency. Right? That's a frequency of 175 RPM. Gives me that allowable shear stress of 14.5 KSI. And I'm trying to find the diameter D. So that's all the information I'm given. Just looking at that, I know, hey, I have that power equation. Power is 2 pi torque frequency. So I can go find a torque, right? I'm given a power and a frequency. I know I can find a torque. My torque is going to be that power over 2 pi f. So the really, really important thing here is keeping these units straight, right? This power is given to us in a horsepower. The frequency is given to us in RPM. These units are not going to match at all and are not going to make any sense for torque if we just plug them in as is. We cannot just say 5 over 175 times 2 pi. Do not do that, right? We want to make sure all of our units match up. So our power needs to be converted into foot-pounds or pound or kip inches. Either one of those is going to work out for us depending on how we convert this frequency. So if I want to convert my horsepower, then I have 550 pound-feet is 1 horsepower. If I multiply that across, that gives me 2750 foot-pounds. Or sorry, foot-pounds per second. Foot-pounds per second. This RPM, since I have this in per second, I want my RPM to be RPS, revolutions per second. So that's 1 per minute. So 1 minute to cancel out 60 seconds is going to give me, oh, I don't think I actually did this calculation. I just included this calculation in my conversion here. So I put it in here. 2750 foot-pounds per second over 2 pi times 175 revolutions per minute times 1 minute has 60 seconds in it. Excellent. So I can get a torque in foot-pounds. This gives me 150 foot-pounds when I plug that in. There's my torque. Now I'm trying to find a required diameter. And I have an allowable shear stress here. And I know that my shear stress, I can relate shear stress as force over area. I can use that to get a diameter, right? Or I can use my shear stress equation that we've been talking about for torsion, which would be the right move here, right? Shear stress max is that torque times C over J. Torque times C over J. So they gave me my T-max in KSI, but I have my torque in foot-pounds. So I'm actually going to go ahead and convert my foot-pounds into kip inches, which, yes, is really annoying. But we have to keep all of these units straight. So I've got 12 inches per foot. That cancels out my foot units. And then I have 1 kip is 1,000 pounds. So that'll give me a torque of 1.8 kip inches, which will work out great with my 14.5 KSI shear stress value. So what other ingredients do I need in my equation here? I have my torque. I have my max shear stress. That is 14.5 KSI. I do not have C. C is what I'm looking for, right? I'm looking for that required diameter. And I know J is going to be pi over 2 C to the 4th, because it told us at the very beginning that this was a solid shaft, solid steel shaft. C to the 4th. So I can plug all of this in to my equation. 14.5 KSI equals 1.8 kip inch times C over pi over 2 C to the 4th. So I can simplify all of that down to solve for my C value, which is 0.429 inches. C is 0.429 inches. But remember, this is actually not my diameter. I misspoke earlier. C is not my diameter. Right? C in my cross section, this is my C value. My C is my radius. So to get my diameter, I actually need to double this. To get my diameter is 0.858 inches. 0.858 inches. Is that it? Find the required diameter of the shaft rounded to the nearest 1/8 inch. Rounded to the nearest 1/8 inch. Now remember, I have to round up whenever it asks me to round to the nearest. It does not mean the actual nearest. It means the nearest required. If I were to round down, then I would have a diameter that is too small, it's undersized, it's going to fail. So I have to round up to the next nearest 1/8 inch, which I believe is 7/8 of an inch. 7/8 of an inch is 0.875 inches. So my actual diameter, if I wanted to get this steel rod off the shop floor, go to Home Depot and buy myself a steel rod, I would buy myself a 7/8 inch steel rod. So for our last example, I'd like you to try this one out on your own before we work through this example together. So the example says the solid steel shaft has a diameter of 25 millimeters. The motor delivers 3 kilowatts of power while turning at 50 revolutions per second. If gears A and B remove 1 kilowatt and 2 kilowatts of power respectively, find the maximum shear stress in regions AB and BC. So the maximum shear stress in the shaft in these two regions, two different shear stresses that we're looking for. So go ahead and take a moment and think about everything we've learned, everything we've discussed in the last video about torque and in this video about power, how you might go about solving this. Go ahead and try it for yourself. So hopefully this was a fairly straightforward example for you using our shear stress and power equations that we've been looking at. Our shear stress max is torque times the outer diameter over the polar moment of inertia, and that our power is 2 pi torque times frequency. So if we solve both of these for torque, we can make that substitution. And I'm going to look at region BC for this calculation. So the max shear stress at BC. If I simplify this equation, I'm going to get the power times c over 2 pi frequency times j. And I'm given everything I need to calculate these values, right? The power in section BC here is 3 kilowatts. It has not lost the 2 kilowatts to B or the 1 kilowatt to A yet, so the power being delivered in the shaft there is the full 3 kilowatts. So that's 3,000 watts times the C of the shaft, which is half of the diameter, right? C is the radius. So if I put that into meters, it's going to be 0.0125 meters, right? Half of the 25 millimeters convert to meters. All over 2 pi times the frequency gave me 50 revolutions per second. Don't need to convert anything there. And then J is 2 pi times C to the 4th power, 0.0125 to the 4th power. So all this one is identifying what you need, rearranging your equations, and then just popping this puppy into your calculator. Simple as that. So the max shear stress we're experiencing in BC is 3.11 megapascals. So hopefully that's the answer you got when you did it. If not, go back and check your math, see if you maybe put something in the calculator wrong. And then the answer for the AB section, I won't work out here. But it is 1.04 megapascals, right? And the key difference here is just noting that you've lost this 2 kilowatts of power. So instead of using the 3,000, you use 1,000 watts in this calculation. Same calculation, just was 1,000 watts instead of 3,000 watts. So hopefully you were able to get those answers. Hopefully that was a fairly straightforward problem for you, just combining those two equations we've been working with. And we'll continue to look at torque in the next few videos with the angle of twist and building on some of these torque concepts.